Unit 3, Chapter 3 is the last chapter in this unit. In this one, we are looking at more specifically some other trends on the periodic table. These trends will help us as we move forward in this class and prepare for later units. As we saw from the previous chapters, that the numbers on the periodic table are important to us. Not all periodic tables have the same information. Many periodic tables will have the atomic number, the atomic mass, and the symbol. The name is something that is sometimes there, but not always there. And then some periodic tables have other information on them. The periodic table that we use has the charges that are commonly associated with that element, and those are in the upper right-hand corner. Other ones have, like the one that we see on this picture here, have the electrons in each energy level, such as those electron configurations that we had done previously. So you can actually see that there's supposed to be 2 in the first orbital, 8 in the second orbital, and 1 in the third orbital. I think that this information is not as necessary as we move forward. That's why I think the charges is just a little bit more. That's why I like using our periodic table for many of the things that we do in our class. But not all periodic tables have the same information. Some of them can again have just the blue arrows, the atomic number, the atomic mass, and then the element symbol. Because you should already know what the name is based on just giving the symbol. Which of the following information about elements is not usually included in the periodic table? Some periodic tables have the periodic tables themselves are colored, meaning they color different groups different colors, such as in here we can see group 1 are the alkali metals. That's something that you will need to know. And so the group 1 alkali metals are that darker orange, whereas group 2A, or group 2 of the alkaline earth metals, are a lighter orange. And then you can see the transition metals are almost like a yellowish orange kind of a color. And you can see some of other ideas or keys over in the corner here. And so other things that we don't see, we can see the non-metals, we can see different colors mean different things within the lettering, and so on and so forth. So sometimes those are used as well. Our periodic table, because of saving of ink, is just black and white, and you can then just make the colors as you want, as you are asked to do actually in coloring the metals, metalloids, and non-metals, in that you were asked to color that. Now you could have another periodic table that has colors for just specific ones, but that's up to you. If you wish to do that, you sure can. And just come up, grab a different periodic table, and use the crayons or the colored pencils that I have available. The alkali metals would have the highest occupied energy level. This should be a reminder from the previous unit. So the nonmetals of group 7A are all called the halogens or halides. The name halogen talks about a Greek word of salt and to be born. Now the halogen lights do have a little bit of actual halogens in them. I believe it is fluorine that is in halogen lights. That is just a little bit, not actually a whole bunch of it. So that is the halogen. That group 17 is another way of naming it as well. We can see group 17 over here as we see all the way down. One of the interesting things also about group 17 is that this group actually has all 3 states of matter. You have fluorine and chlorine being your gases, and then you have bromine as a liquid at room temperature. You have iodine and acetylene as solids. as acetine is more of a metalloid, though, so you also start to see the transition. And if I'm not mistaken, element 117 has been discovered and officially named. What it is at this point, I'm not exactly sure, but it's most likely either a metalloid or most likely a metal-ish in properties, but because it's so radioactive, we'll probably never have to worry about coming in contact with it. But as we can see, the group 7A, they're really close to being those noble gases. Those noble gases are colored in purple over here, and those ones are colored purple because of nobility. So they're almost a has that octet, so they're just one shy. Now, group 8, as I kind of mentioned in the previous slide, the helium, neon, argon are wonderful examples of this noble gases, and they're called noble gases or inert gases because they don't interact or they don't react with other metals, nonmetals, under normal conditions. We have been able to get them to chemically react in extreme conditions. That's usually under lots of heat and or pressure, and therefore that's why their nobility is, because in that type of system, the nobles do not interact or react, so to speak, with any of the common folk, and so they don't work with them, and therefore we don't see them interacting with those. And they're why you call them the noble gases. They also have that full octet. That's where you get the 8, or the octa means 8, part of it as well. Now, here is what you have is what's known as the representative elements. These are the groups in the periodic table that when we talk about trends, as we will be talking about trends, these are the ones that we talk about. We'll see in some later graphs of why we don't talk about the transition metals. We'll discuss them, but we don't really worry about them when it comes to talking about the overall trends, because some things happen in the transition metal that we would have to make exceptions for every single one. And to cut down on some of the exceptions, we talk about the representative groups. So that would be groups 1 through 7, or A, or just 1 through 17 is another way of putting it. In the periodic table, the group B, and if you look on the periodic table that we have, the group Bs are all labeled for you, and the group Bs are known as the transition metals or transition elements. All of the transition elements are also metals, and that's why they're commonly referred to as the transition metals. There are 2 other types of things. You have the transition metals, and then you have the inner transition metals. Those ones are on the bottom of your periodic table. Those are ones that are called the F block. We did not do any of the electron configurations of the F block, but they are there, and so we do need to make sure that we at least acknowledge them. The transition metals, as you can see, have a lot of very precious metals and also metals that we use in our everyday life. So they are an extremely important part of our everyday life, but maybe not representative of some of the trends that we'll be looking at. So the most common ones that we talked about in that transition metal are copper, silver, gold, iron, platinum, and you can name goes on and on. Zinc can be another one. These are ones that you're going to see, and they're going to have that electron configuration in the D block. So they're going to have that start to fill the D block. And we talked about how some of the elements in the D block can have some weird things happening where it would be a half-filled D block, or they kind of pull some different electrons away. But we didn't really worry about that. But that's why we don't look at these for some of the transition metals. They are extremely important, and they do make up a big part of the periodic table, so it is important that we can give them their due. The intertransition metals, not just because they're separated off from the periodic table as they normally would, they are kind of those as the rare earth metals. Although some of them, though called a rare earth metal, are very well known on Earth and are actually fairly common. It's just that we don't want to use them a whole lot. Uranium is a intertransition metal, and you can see inside this drum here that you have uranium, cake uranium, which looks very yellowish, and therefore doesn't seem metallic, but can be broken down, enriched, and put more into a metallic form with that. Most of these are all radioactive, and our contact with them will be very limited. So again, some of the refresh our group names. You will be asked to know these and recall these for your exams, and that is the group 1 are the alkali metals, group 2 are the alkaline earth metals, the group 7A or 17 are known as the halogens or halides, group 8A or 18 is the noble gases. You have the representative groups. I included the noble gases in those representative groups because they do have some things when we talk about the atomic radius. The transition metals, and then our intertransition metals can be sometimes broken down into the lanthanoid and actinoid series. Sometimes you will see these written as lanthanide or actinide series in IDEs. I personally do not like that way of naming them because it kind of indicates some things that we'll talk about in naming, and mainly that it's a non-metal or forms a negative ion, and that's not what they do. They are cations. They are considered to be metals, and therefore they should be named appropriately. So just getting on my soapbox just a little bit for you. But again, this slide, you will be asked to name certain, identify certain elements based on their group name and their family name, or as you might have a last name would be your, like, such as a sir or family name, as these do have. There are other ones, but these ones are the ones that I think are important enough for you to know and be able to regurgitate out to me. Which of the following is incorrectly labeled? Transition metals are characterized as being different than representative elements because they have electrons in which suborbital? Think back from the previous unit. So, talk about the big or the first trend that we talk about in our periodic table, and that is the atomic radius. If you can understand atomic radius, you can understand almost any of the other ones because they all stem or kind of get back from the idea of the atomic radius. Yes, and that's, again, the distance between the two nuclei. How do they actually measure that? Well, that's the thing that they can measure because they know where the nucleus is. Because if we remember back from the previous unit, the nucleus is so big, it's so massive, dense, that that's actually measurable. And so they go under the impression that half of that distance would be the radius, the distance between the two nuclei, because they can find those two parts. Because actually measuring where that last electron is on an atom might be extremely difficult. What would be made a lot easier, as it is again trying to find that nucleus, taking that value and having it. Not extremely maybe the best way, but it's going to get us, at least what we feel as scientists, best case scenario. So as we look at these are the trends that we'll look at. And here are just some values. I'm not going to ask that you know every single value for these. What I want is the overall trend. And that's, to me, what's important, not actual numbers. You can look these numbers up if you really, really, really wanted to. So here is a way to look at it as we see. The trend is it increases as you go down the periodic table. So as you draw circles, like we did for Bohr models, the atomic radius physically has to be drawn bigger because you have to draw bigger and bigger and bigger circles. And it decreases as you go from left to right on our periodic table. Now, if you want to write this on your periodic table, feel free. It's probably a good idea. And as you go from left to right, it decreases. Now, why does that happen? I think that's the part of this that we might have a difficulty with is how does this actually happen, or why does this actually happen? And so what I do is I use an analogy that has these electrons and other things behaving very humanistic, but they're not humanistic and do not have humanistic qualities. But instead I use this analogy that as you say, look at, say, sodium, and one that has a little bit more elements on it, it's going to have 3 rings, it's going to be big, and that one electron on the outside is difficult to see the nucleus, because those 11 electrons are attracted to those 11 protons that are in the nucleus. Well, if you go from sodium to magnesium, you are adding one more proton, but also you're adding one electron. Now those electrons are also in the same circle as well. Now what that does is that brings, or in my mind, or how I think about it, is it brings that inner circle of 2 electrons just a little bit closer, allowing them to be closer to the nucleus and that positive charge, and it gets that second ring that has 8 electrons in it even closer to the nucleus, allowing those outer 2 ones to get even closer to the nucleus. And this happens as we go from left to right, all the way down to when you get to argon, and they're about as close as they possibly can. And then when all of a sudden you go to the next row and go to potassium, you draw another circle, and it expands back out because, oh, I got so much more space. To put this into an analogy that maybe understands is that if you've ever been to a concert and been to a concert early enough so that you saw some of the opening bands, you might see the crowd is just very spread out. And except for if those few people that know that if they want to get close to the stage, they have to do it early. And then as the opening acts get farther or closer and closer to the opening act, and some of them become more and more popular, the crowd becomes closer and closer and closer to the main stage, or the nucleus. And so as these groups get closer and closer, these electrons get closer and closer to the nucleus or to the stage, they are able to pack in a smaller area until, boom, the next concert happens and everybody spreads back out again. And so that's kind of at least how I envision how this works, that they're attracted to that center, that proton heavy center. It has neutrons there, but remember they have no charge, so they're not going to be attracted to the neutrons. And so they're going to get closer and closer and closer until, boom, they add another circle, and therefore they get spread back out again. We can see this happening in here as well, is that as you go from hydrogen to helium, there is a little bit of a change. But then you go from helium way up to lithium, and then what starts happening here is we start to see a overall decrease to neon. Now there's these little blips that we see happening, and those are those anomalies that we worry about. But the overall trend is that as you go from left to right, it decreases. And this is why here we can see this here is why we do not worry about the transition metals when it comes to trends because there are some really weird things that start happening in there, and so we don't worry about them when these talking about these overall trends. But they, for the most part, even still hold true to those overall trends, is that when you go from left to right, they decrease, and as you go down the group, that increases. Which of the following sequences is correct for atomic size? So, one of the things that we should understand is that metals tend to lose electrons to obtain a positive charge and therefore have a cation. And one way you could remember that a cation is positive is that cats have paws. Meow. And therefore paws and scratching and all that stuff. And so cations are positive, and so you can have that little paw. So cations are positive from their paw. Nonmetals gain electrons and to get that negative charge, and as that happens, they are called an anion. Well, anion would be anti or negative, is how you might think about it, is that anions are negative because anti so-and-so, or anti-homework. I don't know why anyone would be, but if you were anti-homework, that means you're against homework. I don't know why anyone would be that way, but that's kind of the analogy that one might be able to use. When this happens, we can see that the atomic radius also changes, and that's based on, again, you have less competition for that positive charge. The atomic radius decreases when you have more electrons there, because like charges repel, they balloon up or they get bigger. Now, this gaining or losing and the likelihood of this happening, it sometimes adds into what's known as ionization energy. And that's the energy required to remove one electron from a gaseous atom of this element. Now, what happens here is it increases as you go from left to right, and it decreases as you go down a group. And so if we look at what happens to the atomic radius, as you go down the group for atomic radius, the atoms get bigger and bigger and bigger. When you talk about ionization energy, you go down the group, it gets easier and easier and easier to pull an electron away. Why? Well, if that one electron is farther and farther and farther away from that nucleus, it's easier for that electron to be lost or removed, because it's like, well, I'm not going to see any of that positive charge because they all got all these other people in front of me. And so that happens. Now, there again are an exception, but that's what it works with. And there's a later slide that we'll see that these are inversely proportional. So as atomic radius goes up, ionization energy goes down. And so they're inversely, so one goes up, one goes down. That's why I said understanding the atomic radius is so important. Here's another way to look at it, but definitely make sure that you pay attention to the terminology that is being used here, and that the energy generally increases as you go from left to right. Why? Well, as the atomic radius gets smaller and smaller and smaller, those electrons get closer and closer and closer to the positive nucleus, and therefore make it more and more difficult to remove. Now, something else that's happening is they're getting closer and closer to achieving their octet, or those 8 electrons in that outer shell, and that also has something to do with it. But I like the analogy of the atomic radius because then it reminds us of what's happening with that trend as well. You can see these trends here as we look, that the energy to remove one hydrogen atom, which is only one of them, is actually pretty big when it comes to removing them. helium, which only has two, it becomes very difficult. Lithium, very easy to remove the one, and as we look at ones that are in that first group, so hydrogen, lithium, and sodium, so as we just go down those, it gets harder to, or easier, less energy to remove an electron. When we look at group 8, which is way on the other end, we have these, and as we look, oh, that might mean that argon has chemically bonded. Probably has at this point. But krypton, xenon, and radon definitely are contenders when it comes to removing electrons or doing some other things. What other things we can see here is where we start getting into the next level, in that we can see that lithium, trying to take lithium's third electron, is very difficult, because we can see that is a lot of energy, kilojoules per mole. That is a lot of energy, and that's why we say it's probably not going to happen. Lithium will lose 1, 2 is pretty hard, 3 is almost impossible. And as you can kind of see, for beryllium, it has 2 in the second energy level, and that 1 is pretty easy. 2, it takes a little bit, but yeah, good luck getting that third away from beryllium as well. So these trends do happen. Again, we can look up all these values if you really wanted to. So if we needed to, we could. By looking at this, we can again see that overall trend, and why we only talk about the transition the representative metals and not the transition metals is, again, these crazy things that are happening. We also see those anomalies within that we talk about, but again, I want to know, do you understand the basic trend? As you go from left to right, the ionization energy is increasing. Yes, there are some things that happen, but it does not matter. As you go from left to right, those are increasing. As you go down a group, the ionization energy goes down. Metals tend to now, electronegativity is the ability of an atom to gain an electron. As we saw that, hey, guess what? Some elements lose. Well, if someone's going to lose something, if someone's going to lose $100, someone's probably going to pick up that $100. Same idea with the electrons. There's an element out there that's going to be losing electrons. There's definitely going to probably be an element that's looking to gain, and that's the nonmetals. They're likely to gain those electrons that the metals lose. So, and it still follows that same path, is that as you go from the top to the bottom, the values actually get less and less and less and less, for the representative elements at least. And then as that happens, as you go from left to right, the electronegativity values go increase and increase and increase as those happen, which again is inverse to what we see with the trend with the atomic radius. As the atomic radius gets bigger, as you go down a group, the atomic or the electronegativity increases as that happens. So they're inversely proportional when those things happen, or at least those values are inversely proportional as you look at how these things happen. Here's a chart of electronegativity values. We also notice that there are no group 18 elements, and that's because they're not going to give up, or they're not going to take on any electrons, because they have their octet. And so we can see these values here. Again, not a thing that you need to write down. A lot of times these electronegativity values would be given to you, and therefore you just kind of have to know where to look for them. And they are out there. Heck, you could Google it up if you wanted to, and you would be able to achieve these. But what we can see as we go down the periodic table, we can see that the electronegativity decreases as we go down and increases as we go from left to right. Usually what the identifiers are, francium, which isn't even on here, would have the lowest, and fluorine has the highest at a 4.0. Just like a grade point average. Here's a bigger chart, and you can see based on how the shading happens is what is increasing. And so as we go from top to bottom, the atomic radius gets bigger, therefore the shading gets darker as we go down. As we go from left to right, the atomic radius gets smaller and smaller and smaller, and therefore the shading gets less and less and less. Where the other ones are quite opposite, where as you go down the periodic table, they become less and less. As you go from left to right, they become more and more. Good probably thing to look at, or even write down on your periodic table as you are preparing yourself, not just for the Chapter 3 quiz, but also the Unit 1 quiz. Which of the following is the most electronegative? Now that concludes the Unit 3 periodic table. The next unit will focus on covalent compounds and covalent bonding, and some of these things that we talked about in this unit will be used very quickly.